All right, let's talk about one of the trickiest parts of calculus, integration by parts. But don't even worry about it, because today I'm going to let you in on a little secret. It's a powerful shortcut, a true secret weapon that turns what's usually a complicated mess into something clean, fast, and believe it or not, kind of fun. So let's just dive right in and see how this thing works. So you know the feeling, right? You're deep into a calculus problem and you have to use integration by parts, and then you have to do it again. And again, your page just explodes with u's and v's, integrals inside of other integrals, and it is so easy to just drop one little negative sign and boom, the whole thing is wrong. Well, it's super frustrating. And here's the culprit, the classic formula. Now, don't get me wrong, it's powerful stuff. But when you have to use it more than once on the same problem, it kicks off this massive chain reaction of algebra. You solve one integral just to find, hey, look, another integral. It's a process that feels totally chaotic, and honestly, it's just asking for you to make a tiny mistake.
Okay, but what if there was a better way? A way to organize all that chaos and just get to the right answer without the headache? Well, good news, there is. And we're about to get into it. It's the simple DI method. Now, what's so cool about this is that the tabular method isn't some brand new, complicated math. It's really just a brilliant way to stay organized. Think of it like a filing system. It takes that super repetitive process of integration by parts and just lays it all out neatly in a table. And the best part? You can forget about rewriting that messy formula over and over. And this is what that beautiful organization looks like. Seriously, it's just a simple 3-column table. That's it. First column, you just alternate signs. Plus, minus, plus, minus. Easy. The second column is our D column. That's for the part you're going to differentiate. And the third is the I column, for the part you're going to integrate. See? Super straightforward.
Okay, theory is great, but the best way to really get this is to see it work. So let's solve a classic problem together, the integral of x squared times cosine of x. All right, step 1. We've got to make our choices. Which part goes in the D column and which goes in the I column? Well, there's a really handy rule of thumb called LIATE. It stands for logs, inverse trig, algebraic, trig, and exponential. You just follow that order to pick your D term. In our case, x squared is algebraic and cosine of x is trig. A comes before t, so we're going to put x squared in the D column. The goal here is to pick something that will eventually differentiate down to 0, and polynomials are perfect for that. Okay, now for the easy part. We just fill out the D column by taking derivatives all the way down. We start with x squared. Its derivative, 2x. The derivative of 2x, just 2. And the derivative of 2 is 0. And that's it. That's our signal to stop. Super simple. Next up, we do the same thing for the I column, but with integration. We just have to integrate the same number of times we differentiated. So the integral of cosine of x is sine of x. The integral of that is negative cosine of x. And one more time, the integral of negative cosine of x is negative sine of x. And just like that, our table is all filled out. Okay, get ready, because this is where the magic happens. To get our answer, all we have to do is multiply along the diagonals. You follow these arrows, you take the sign from the first column, multiply it by the term in the D column, and then multiply that by the term that's one row down in the I column. We're just going to do that for each row until we've used up all our terms. And now we just assemble our answer. Let's just write out those products we just found. Our first diagonal gives us plus x squared times sine of x. The second one, now watch the signs here, is minus 2x times negative cosine of x, so that double negative makes it plus 2x cos x. And our last diagonal is plus 2 times negative sine of x. String them all together, don't forget your plus c, and there it is. That's your answer. Look at that. No messy algebra, just a perfectly clean solution. Okay, that worked perfectly. But you might be wondering, what happens if that D column never hits 0? Well, that's a great question. That's what we call a cyclic integral, and it just needs one little tweak to our method. Let's check it out. So why is this even a thing? It all comes down to the types of functions we're dealing with. Think about it. Polynomials, like our x squared, are great because you keep taking derivatives and eventually, poof, they vanish and become 0. But other functions like e to the x or sine and cosine, well, they're different. You can differentiate them forever, and they'll just keep cycling through different versions of themselves. They never go away. So what do?
The process has this really clever little twist. You start out the same way, multiplying down the diagonals. But when you get to the last row you've calculated, you stop. And instead of going diagonally, you multiply straight across, horizontally. Sine times d times I. Now here's the trick. That horizontal product goes back inside an integral. What this does is it sets up an equation where you have your original integral on both sides, and you can just solve for it, just like a basic algebra problem. All right, so to wrap this all up and make sure you've got this method down cold, let's just go over the key rules one more time. This is what you need to master it. Think of these as your 3 golden rules. Rule number 1, choose your D term wisely. Let the LIATA rule be your guide. You want the thing that's going to simplify the best. Rule number 2, know when to stop. For most problems, that's when your D column hits 0. And rule number 3, remember the horizontal rule. If you're dealing with one of those cyclic integrals that never hits 0, your very last term is the integral of that final row multiplied straight across.
You know, there's this great quote from Engg that says, "The essence of mathematics is not to make simple things complicated, but to make complicated things simple." And that perfectly nails what the tabular method is all about, right? It's not new math. It's just a new way of looking at the problem, a way to take something that feels really messy and make it elegant and simple. So there you have it, a powerful, super elegant shortcut for what is usually one of the biggest headaches in calculus. The next time you're faced with a big, ugly integration by parts problem, you'll have this secret weapon in your back pocket ready to go. So the only question left is, what problems are you going to go solve with it?